So great. Where does entropy come from? What's the molecular origin of enthalpy and entropy? How can we actually count how much entropy is going on? Sure, we can say if it's more disorder, there's more entropy, but what are the underpinnings of entropy? And can we understand them well enough to start calculating entropies in the same way we can calculate enthalpies? Well, we know enthalpy comes from bonds making and breaking. Right? We can measure the remember we can look actually have a pretty good estimate of the change in enthalpy of reaction just by looking at the strength of the bonds involved. Non-covalent interactions created by electrostatic force, right? You can, by looking at the electrostatic interaction of ions as they come together, enthalpy comes from those. The mechanical work required to move atoms around, if you think about, pressure volume work, that we have enthalpy changes due to the mechanical work needed to move moving atoms around by pressure. But where does entropy come from? What are the molecular details of entropy that allow us to make calculations with those? So it's randomness. Great. Okay, fine. More randomness is more entropy, but we want to measure randomness. How do we do that? How do we compute the degree of randomness there is? So the entropy comes from the number of states accessible for the molecules to move around in. If you could think of a lattice of a crystal that has or some molecule that has two parts that you can tell apart from each other. Then at each portion in this, at each position, it could be in either one state or the other state. And so there's multiple states possible. For each individual location on the lattice, there's two states possible. Or if you think about an ideal gas, if you simplify it and think that you divide up space into little cubes, and then to a decent approximation, then each molecule at any given time is in its own cube. And so the number of states that are available for the molecules will be proportional to the number of cubes there are available. If it's an ideal gas, you don't really need to worry about them colliding into each other. So to a good approximation, that if you double the number of cubes, if you double the volume, then you have twice as many states available to be in. Okay. Or here's an example. If you think about this crystal lattice that I talked about, where you have molecules that actually carbon monoxide does this at low temperatures near absolute zero. You could light up, with the carbon in one direction, the oxygen in the other direction, and it's about the same energy. They're very close to the same energy. You can treat it essentially as equal energy sides. So if they're all lined up, with the carbon pointing one way, you got 20 tails and zero heads and zero tails. But you could also imagine them just sort of lined up randomly. Here on this side I have 9 heads and 11 tails. Now, if it just happens by random, in which situation is there going to be, which situation is more likely? If you just, threw them in, let them find their lattice positions, what are the different likelihoods? Well, how many ways are there to be arranged with perfect ordering versus mostly disordered? Well, in this case, there's only one way for all the heads to be pointing up and down. We're assuming that the molecules are indistinguishable as they are. They're just made of every carbon, assuming the same isotope, and oxygen is the same. So you got 20 heads and tails, but it turns out that there's 167,960 ways to have 9 heads and 11 tails. And so if it just randomly happens to be one way or the other, generally it's going to be in a more disordered state. So what we can do is we can actually start counting how many states there are. It's going to be 167,960 times more likely to be in that second state. And that ends up, that ratio ends up being a good measure of being highly related to the entropy. What we want to, it turns out that the entropy is not equal to the number of states. For various reasons, that ends up not being additive like we know entropy is. But it turns out that entropy is proportional to the logarithm of the number of states. And there's a very clear constant proportionality. So entropy is proportional to the logarithm of the number of possible ways of arranging it. So here, entropy is S, how we usually denote it. So this omega, sometimes it's written as W as well. They're both the same things, is the number of ways. And we call the number of ways to arrange the parts of the system microstates. consistent with the macro states, i.e. the value of the energy or the volume of number of particles. So we know the number of particles in a system, and we say, well, that's the macro state. There's a certain number of particles, they're in a certain volume, they have a certain energy. Great. How many ways are there to arrange the particles with that energy, that volume, and that number of that energy, that volume, and that number of particles? And that is the density of states. Which is just another way of saying the number of ways to arrange it consistent with that. Okay, so then K is actually something we've seen before. It's the gas constant divided by Avogadro's number. So this, this is not an accident or anything. The reason we see the ideal gas constant popping up in ideal gases is that most of those ideal gas formulas can be derived from Boltzmann's equation. Ideal gases have no enthalpy, right? They just occupy space and move around. So it makes sense that most of the properties come from the entropy of those systems. So it's not that we're seeing the ideal gas constant here up here in Boltzmann's equation. It's that Boltzmann's constant is appearing in the ideal gas formula. It's the Boltzmann's constants that's the fundamental thing. And to some extent, you could think of really, Boltzmann's constant is just a measure, a different way of thinking about what the temperature is. So let's remember the gas constant is. Let's figure out units of entropy here. So yeah, so that's the gas constant when Na is Avogadro's number. So let's look and see what units Boltzmann's constants has. So we start with the gas constant, right? So that's 8.314 joules per mole Kelvin. And Avogadro's number is things per mole. Things don't have a unit. So it's just things per 1 over mole. So the moles cancel. And so Boltzmann's constant has units of joules per Kelvin. So really the choice of the temperature scale is really what sets Boltzmann's constant. Cool. Okay. So so it's essentially a way of it's an arbitrary constant that depends on our temperature scale. We could decide to set Boltzmann's constant equals 1 if we set the right temperature. Okay. Those would not be very useful temperature units to use, but they would show that really entropy is fundamentally just the logarithm of the number of states. But to fit into the set of units we already have, we have to multiply by Boltzmann's constant. So entropy is equal to Boltzmann's constant times the logarithm of the number of states. All right, so let's do a little bit more quantitative work with macrostates and probability. So here you can imagine that we have 3 possible states, one with all the molecules in you have 2 gases connected by a stopcock. You have it can be open or closed. And state A, all of the molecules are in one of the 2 vessels. In state B, they're in the other 2 vessels. And state C, they're evenly divided between the 2. And so you can think of these as macro states, like how many particles are in on one side or the other side. So state A is one macrostate, it has 4 particles on one. State B is another, and has 4 particles on the other. And state C has 2 particles on each side. So there's only one way to arrange the molecules here consistent with the macrostate. 4 particles, there's 4 particles there. There's only one way to do that. For state B, there's again only one way to arrange molecules. There's 4 on one side and that's it. State C, however, those 6, right? If we number them 1 through 4, and they're number them 1 through 4, then we could have 1 and 2 on one side. We could have 1 on 3 on one side. We could have 1 on 4. We could have 2 and 3. We could have 2 and 4. We could have 3 and 6. And so you have actually 6 possibilities there. State C is 6 times more likely. So let's actually go through and calculate an entropy here. Here, the entropy is going to be Kb log, what's the number of states? 1, so the entropy is 0. Again, here the entropy is 0. In this case, the entropy equals Kb log of 6. We won't try to multiply that out, but that would be the entropy of that state. Kb ends up being very small because it's the gas constant divided by Avogadro's number. So it's down like 10 to the 19th or so. And so we're not 10 to the minus 19. And so that's not very, and if you're just looking at differences between one way and six ways, there's not very much entropy. But usually we're dealing with, Avogadro's numbers of molecules, different numbers of states. So the entropy does start to be significant. Okay. So let's actually do some calculations. So solid carbon monoxide can pack in two ways, with carbon up or carbon down. So what would the molar entropy of carbon monoxide be at 0 Kelvin? So for one molecule, the number of configurations is 2, could be up or down, right? For two molecules, well, up or down times up or down, that's 4. And so for n molecules, then the number of different configurations is 2 to the nth. So we can plug this in to get the entropy of 1 mole of molecules. So we have entropy equals Kb log of 2 to the n. And now remember, logarithm is something with an exponent we can just write as Kb times, we'll call this Na, since specifically it's a mole of a mole of particles, and Na log of 2, right? Because log of 2 to the Na is just Na times log of 2. And of course, Kb is just the gas constant over Avogadro's number. So this is equal to R log 2, just by the definition of Boltzmann's constant. And plugging this in now we're actually at a place we can plug in numbers. This is 8.314 joules per mole Kelvin, and log of 2 is 0.6. Now remember, this is a natural log, not a log base 10. I mean, in theory, you could use, right, a log base 10, because then you'd have a different multiplicative constant, but it's much easier to just use natural log in most cases. So 9.3, and that has no numbers, right? It's the log of a number, so it has no numbers. And so the answer ends up being, plugging in, is 5.76 joules per mole Kelvin. Now it is an entropy per mole because we multiplied by Avogadro's number. So experimentally, it ends up being about 6 joules per mole Kelvin. So this is a pretty good estimate. Just by counting the states, we can figure out how much entropy there is.